Okay, welcome back to Empirical Economics. Before we start right away, I would like to make one announcement because today is going to be my final lecture at university because I'm switching over to industry. So this will be the last time that we see each other in here. After next week, you will stick to Mr. Trede and he will teach you all the rest about empirical economics. So I enjoyed it very much, although we didn't have direct interaction. Thanks anyway, and enjoy this lecture and of course enjoy all the other lectures and the rest of your studies. We wanted to give you the opportunity to ask questions in the last week and to discuss these questions, at least to an extent, today. And we received questions mainly regarding the significance level, the p-value, confidence intervals, what do all these values mean, what is the critical value, and so on. So I prepared a little R file, a little code file that should show you graphically what's going on there and how you can interpret all these values and how we actually end up with all these topics. So let me just share my screen, and you should see or should be able to see right now a plot that you have seen probably every single lecture now, namely the plot of district average class size on the x-axis and district average test score on the y-axis, something that we encounter on a daily basis because we want to find out what's the relation between class size and test score. And what we have done so far is to run a regression and plot the regression line. We computed the intercept and we computed the slope coefficient of that line, and we already saw that there seems to be a negative dependence between class size on the one hand and test score on the other hand. So larger classes tend to have a worse test score. Obviously, we don't know about that relationship. We can only estimate it from data, but for now, for the sake of this argument, just think of the red line as the true regression line, as the population regression line, the one we actually don't know, but we now just assume that this is the true regression line, that we know that true regression line, okay? Just bear that in mind for the next quarter of an hour. Having said that, we also said that all the randomness that we talked about, that everything we talked about in our estimators, that they have a distribution that we can, because they have a distribution, conduct t-tests, that we can compute confidence intervals, that all of that came from the fact that we do not observe the whole world as it is, but that we only observe a single sample, a single data set. And of course, we can also observe other data sets. If we rerun the whole experiment, the whole gathering of the California test school data set 10 years later, we would have a different data set and we might have a different outcome. If we do that again 10 years later and again 10 years later, we obtain different data sets, and in each data set, we might have a different outcome. We can do that, of course, physically by just waiting a long period of time, then these two data sets might be independent. But we can also do that in our computer with R by, instead of physically asking people after that for their test scores, we can just take the whole data set and randomly redraw points from the data set. So we resample the data set, and instead of selecting each point one time, we have certain points that we don't select and certain points that we might select 2 times, 3 times, and so on. So for example, one resampling might look like this. We only select these blue points, just completely at random. All of the points have the same probability to be chosen. So some points won't be chosen. This black dot over here has not been chosen. This blue dot has been chosen. It might have been chosen 2 times. This is called resampling. And with this, we get a new sample, a new data set. And based on that data set, we can continue and again estimate the relationship between average class size and average test score. And as you can see here, this relation now is different. We have a slightly different intercept, but even more important, we have a slightly different slope coefficient. And if we do that again, resample again, resample again, and again, and again, and again, do that multiple times over and over again, we always, most likely always get a different slope coefficient and a different intercept. And here they are very similar, but they can also be quite distinct like they are in here. In here we have a much distinct intercept and a much flatter slope coefficient. So the randomness in our estimator comes from the fact that we only obtain a sample of the world and not the whole world itself. So we can ask ourselves, can we, because we don't know the red line, can we find out how uncertain we are about our estimator, how uncertain we are about the value we assigned to the slope coefficient? And that led us to the topic of confidence intervals, where we wanted to create now not just a single number, but a whole interval, a range of numbers that covers our true value with a certain probability. So that includes this red slope coefficient with a certain probability of 1 minus our significance level, and that significance level in most cases is 5%. So the red value here will be covered with a large probability of, for example, say 95%. And then we did that. We came up with a formula how to compute the confidence interval. That was the point estimate plus some critical value. We'll come to the critical value in a minute. Plus minus the critical value times the standard error of our estimator. So the uncertainty connected to the estimation process. And when we do that, we come to a different plot, namely this plot here. What we get here is on the left-hand side, the same thing you've seen before. We have the true value, the red one. We have a resample, and from the resample, we computed our estimator. And from the estimator, using the critical value, again, we'll talk about that in a minute, we computed a confidence interval. On the right-hand side, you can see the red line is the true value of the slope parameter. It's minus 2.2 something. I think minus 2.29 or something. Our new point estimate, our new estimate here is minus 1.9-ish something. And the confidence interval that we created actually covers the true value. So the confidence interval we computed now definitely covers the true value. And we know that because in this case, we assume to know the true value, which in reality, we don't. If we now would do this again, over and over again, so resample, compute the blue line, from the blue line, compute the confidence interval, we might end up with a plot that looks like this. We have changing values of our estimates. We have, of course, changing confidence intervals. And on the right-hand side, I've plotted all the confidence intervals that we have seen so far. And as you can see here, here is the first confidence interval that does not cover the true value. So not all of these confidence intervals cover the true value, but only a fraction of, if we do this very often, in this case, 95% of all the confidence intervals will cover the true value. So if we run this, now if we wait just a little bit until the 100 iterations will be finished, we might see, unfortunately, purple is not the best color to judge this. So we have one interval that misses the true value, the second interval that misses the true value, the third and the fourth interval, these two miss the true value, and maybe we will end up with 5 of 100 confidence interval that miss the true value. We might get 6, we might get 4, we might get 7, we might get 3. It's all, of course, possible because we only did this for 100 times. In this case, it seems to be that we are lucky. No, we're not. So 6 out of the 100 confidence intervals in here did not include the true value. If we do this not 100 times, but 1,000, 10,000, or 1,000,000 times, we would expect that on average 5 out of 100 confidence intervals will not cover the true value. And if I go back 3 plots, we see this confidence interval here really does not cover the true value. So the true value is out of this confidence interval, and that's not good, but the probability of doing so, that probability is limited to our significance level, to a value we can choose, depending on how well the data is, how sure we want to be that the true value is not excluded in the confidence interval. I said this uncertainty, this sampling uncertainty, gives us or delivers the fact that our OLS estimator has a distribution itself. And we said in the previous weeks that the asymptotic distribution or the approximate distribution of the OLS estimator is a normal distribution. So in large samples, and this sample here is 420 school districts, so that is large enough for that approximation. This distribution is normal. Oh, sorry. So let's have a look whether this is true, whether or not this is true. And this one here is the histogram. And I did that before because it takes a couple of seconds or minutes, of 10,000 resampling steps or iterations. And in each iteration, I ran a regression and I obtained an estimate for the slope coefficient. As you can see here, most slope coefficients were around minus 2.3, that area. So the value we already know is the true value. And if I want to fit now the curve, the density function of a normal distribution to that plot, we see that this almost perfectly fits to the density function of a normal distribution with certain variance and with expectation of the true value that we, in this case, assume to know. This distribution of the OLS estimator then leads to the fact that if we compute the t-statistics of any, to test any hypothesis, that this t-statistics also has a distribution because it's the OLS estimator minus something, minus a constant, divided by a constant. So that is also a random variable, and that also has a distribution, which is very nice because we can then look at this distribution. Now, the distribution I want to look at, the test I want to conduct is our beta 1, is that equal to minus 2.29? So the value we just know is the true value. So let's have a short look at this. On the left-hand side, we see the distribution of the OLS estimator. And on the right-hand side, we see the distribution of all the 10,000 t-tests. Now, the t-tests conducted or generated by all the 10,000 resampled regressions for the hypothesis that beta 1 is equal to minus 2.2943. That is the value we would get if we run the regression for the whole sample that we initially had. And then we see the t-test, well, it's distributed as, in this case, a standard normal distribution. So it's centered around 0, as you can see here. And the largest values we obtain are somewhere around +3, and the smallest values are somewhere around -3, a little larger in absolute value. In this case, you can see that some values obviously are very unlikely to happen. And although we know that the value that generated this t-statistics has a beta 1 of minus 2.29, we now want to state that if we obtain a t-value that is so far in the outskirts of the distribution, that this should pose significant information and significant facts that we can actually reject this null hypothesis that the true value is minus 2.29. But we want to limit the probability of making that error, because obviously a t-statistics of minus 10,000 is also possible because the normal distribution isn't limited to any area. So we might make this mistake just by chance because we obtained the wrong sample or a bad sample. A sample that, although the true value really is minus 2.3, the sample yields a t-statistic that is, for example, minus 3. We want to limit that error, and we want to limit that error to, for example, 5%. So we only exclude or we only reject these hypotheses where we are really in the far outskirts or tails of the distribution. So, for example, in the left 2.5 or right 2.5% of all the distribution. And then we would have limited the probability of making an error to 5%. Now the left 2.5 and right 2.5% of the standard normal distribution are exactly everything left of 1.96 and left of minus 1.96 and right of plus 1.96, which is the reason why we have this 1.96 as a critical value. If we want to have a different significance level, so if we want to limit the probability that we wrongly reject a null hypothesis just by chance to, for example, 1%, then we would have different critical values that are even further outside, even further in the tails of the distributions. Now, from the critical values, we can also switch to the p-value, something that you also wanted an interpretation for. So in this case, let's not look at the hypothesis to test that beta 1 is equal to minus 2.29, but let's check the hypothesis that beta 1 is equal to 0. We can state the hypothesis, and we can compute the t-statistics for this hypothesis. And again, we can do this over and over. And if we did that for the 10,000 regressions, we would end up with a distribution of t-statistics that looks like this. It ranges from minus 8 somewhere up to minus 0.9 or somewhere in the region. Again, the thing we stated before holds also true. If the null hypothesis is true, then we would expect this distribution of t-statistics to look like this, like a standard normal distribution. So obviously, these two distributions differ quite a lot from each other. But normally, you won't see the whole distribution of t-tests, but you will only, in a regression setting and in a setting where you analyze a data set and find out the relation between the variables, you will of course only end up with a single t-statistics, not with many t-statistics, right? For example, you might run the regression, compute the t-statistics of the test of the hypothesis that beta 1 is equal to 0, and you will end up with a t-statistics of minus 4.2. Then the p-value is the probability of, if the null hypothesis is true, so if we have this distribution of being out in the outer tails of this distribution, namely being left of minus 4.2 or being right of plus 4.2. So in the very outer tails of this distribution, and the probability of being there is very, very low. It's 0.002%. So the probability of wrongly rejecting the null hypothesis here just by chance, just by random sampling, is very small. So you have a strong signal that the null hypothesis is in fact wrong and that you can actually reject the null. If we, for example, observe a t-statistics that is minus 2.2, so this purple one over here, then what we see is that we still are in the outer parts, in the outer tail of the distribution, but there is some even visible probability to reject the null hypothesis, although it is true. And in this case, the p-value would be this area on the bottom left between under the red curve, left of the purple line, and under the red curve, right of the purple line. And these two areas add up to roughly 2.8%. So still a value smaller than your standard confidence, your standard significance level of 5%. So you can still reject the null hypothesis of beta 1 being equal to 0 at the 5% level. I hope that these graphs and plots gave you more insight onto the topic, and that they pretty much answer the question that you stated in the email, and that we can continue now with Mr. Trede and nonlinear regressions. Oh, and by the way, of course, we will have an active break today at a point that we will basically see maybe after Mr. Trede's slides, so when we are switching over to me again.
All right, thank you, Andreas. Are there any questions concerning the part you've just heard? So it's really important to understand this dual nature of test statistics and confidence intervals. So on the one hand side, you have the confidence interval, which is created before you actually have got the data, in which case you have 95% probability, as Andreas showed in the simulations, of covering the true value. But once you have actually drawn the data and calculated the value of the test statistic, then it's just a number, and you can't say that the probability is 95% that the true value is covered by the confidence interval. And the same is actually the case for test statistics. So the test statistic has a dual nature as well. So on the one hand side, it's a random variable because you compute it from the data. Before you actually draw the data, it's random because the data are random. But once you've drawn the data, it's realized, and then it's just a number. And the p-value and the confidence level, those are probabilities, but they only refer to the pre-sampling It's really important, and don't be shy to ask again. We know that this is the critical point in understanding how statistics work. Okay, so the next topic is an extension of the multiple linear regression model that we've already seen before. Up to now, as you might remember, everything we did was looking at a linear regression. So we had a simple linear regression model where the endogenous variable was just a linear function of the regressor. And we had a multiple linear regression model where the endogenous variable is a linear function of all regressors. But of course, approximating the true relationship between the endogenous variable on the one hand side and the regressors on the other side approximating this by a linear function might not always be appropriate. I think everybody agrees that if at all, the relationship between the endogenous variable and the regressors can only be approximated by a linear function, and often actually it can be approximated by such a function, but sometimes it cannot. And that's actually quite often the case in economics, because if you think about what you learned in microeconomics, you learned about the decreasing marginal utility. So a utility function is in its very nature, by its very nature, it's a nonlinear function because the marginal utility is decreasing in the amount of goods that you actually consume. And in the same way, if you look at a production function, you have a decreasing marginal product of each input factor. So again, it's not a linear relationship between the inputs and the output. So even from economic theory, which is not often the case, but here we can actually say that even from economic theory, it's obvious, or it should be obvious, that the relationship between the endogenous variable and the regressors need not be linear. And in these cases, actually, we would a priori reject the assumption of linearity. So a production function as a linear function is in general not a very good idea, as economic theory, macroeconomic theory will tell. Okay, so why do we still work with multiple linear regression models, even though we know that in some situations this assumption of linearity might be violated? And the answer is that it's surprisingly easy to reformulate the multiple linear regression models to take into account nonlinear functions. And this is what we are going to talk about today. So there are three questions we would like to tackle. The first one is, how can we actually detect nonlinearity? How can we decide whether nonlinearity might be a problem or not? Second, we ask ourselves, what are the consequences of nonlinearity? So is it really a severe problem, or could we just ignore that? And finally, how can we modify the multiple linear regression framework to take into account, to explicitly take into account nonlinear relationships between x and y, or x's and y's? So these three questions will be talked about next. So let's first think about how could we detect the nonlinear relationship between a regressor and the endogenous variable. And as Andreas already said, you've seen this plot many times before, and you're seeing it again now. This is, again, the class size on the x-axis and the test score on the y-axis. And you remember that we had a linear relationship which we fitted to this cloud. But if you look at this cloud and squint your eyes, then you might say that, well, of course, it's not on a line, but the points are scattering around a linear relationship relatively clearly, I would say. They scatter around a lot, but if you squint your eyes, then the assumption of a line, of a straight line through this cloud of points does not seem widely absurd. Okay? So it's a reasonable assumption. While if you look at this plot, where we have the test score again on the y-axis, that's the endogenous variable, but where we have the district income in 1,000 US dollars on the x-axis, if you squint your eyes here, you will see that the average relationship between the district income and the test score cannot be approximated in a sufficiently nice way by a straight line. If we did that, like here, that's really the fitted best linear relationship between the axis, the district income, and the test scores here. If we did that, you see that, well, this line does not really approximate the underlying relationship between income and test scores in a sufficiently appropriate way. Okay, so if you squint your eyes here, then you will see that while the relationship looks somewhat like, it's relatively hard to place this dot, something like this. So it goes up relatively steeply here and then flattens off towards the right end of the distribution. So it's a banded curve, if you want. Okay. So to answer the first question, how can we detect nonlinearity? Our suggestion is to really plot the relationship between, or the scatter plots between the regressors, one regressor at a time, and the endogenous variable. And then take a close look at that plot and say whether you, by squinting your eyes, whether you see a nonlinear relationship between these variables or whether a linear relationship seems reasonable. Okay? So it's a visual approach, a graphical approach to detecting nonlinearity. We know that this approach is in a way not really scientific because different persons might have different impressions of these plots, but at least in these two examples, I think everybody would agree that here a linear relationship is reasonable, while here it's not. And if you really feel that this kind of intuitive approach to nonlinearity is not sufficient and you want a more formal test approach, then you're invited to visit the course on econometrics, where we present a more formal way of testing nonlinearity. All right. So, but here, this visual graphical approach, I think, is a good idea to understand what's actually going on. All right. So the next question is, could we just ignore this problem? What are the consequences of nonlinearity between the regressor and the endogenous variable? And the answer is, no, we should not ignore this problem, because if we have nonlinearity, then the effect of a change in the regressor x on the endogenous variable y depends on the value of the regressor. Or if we have multiple regressors, it depends on the value of all the regressors. So in other words, the effect of a change on of a regressor on the change of the endogenous variable is not constant. Okay? This effect used to be constant in a multiple linear regression, and the coefficients, the beta 1, beta 2, and so on, these were the effects of a change in the underlying regressors. But if we look at a nonlinear regression model, this change depends on the values of the regressors. So the marginal effect, to put it in economic terms, the marginal effect is not constant. It's not everywhere the same. It depends on where you are. So the marginal product of a certain input factor, say labor, depends on the endowment that the firm has in terms of labor and capital, and which other input factors you have. And that means that if you specify a linear model, as we did before, then the functional form is not correct. So we assume, or we pretend that the relationship between x and y is linear, which means that we pretend that the marginal effect is constant, but in reality, it's not. And therefore, if we want to use the results of our regression analysis for policy advice, then we would incorrectly estimate the causal effect of the regressor on the endogenous variable, which means that we think that the causal effect of x and on y is, say, beta, but in reality, it's not always beta, but it depends on whether x is small or large. So to go back to the previous slide, if we pretended that the marginal effect is constant and the slope of this red line, then we would say the marginal effect of increasing the district's income, ceteris paribus, is, well, the slope of this line. But we can see, if we look at the scatter plot, that the marginal effect down here is higher, while the marginal effect up here is smaller than the slope of the red line. So our policy advice would be based on the slope of the red line, but that's not the correct slope. The slope is steeper here, and the slope is less steep up here. And therefore, our policy advice would be wrong, would be misguided. Okay, and we shouldn't do that. So it's really a severe problem and we should do something about that. And the solution is relatively easy. The solution is that we estimate a nonlinear model. What do these nonlinear models look like? Well, let's start with the most general form. In the most general form, the linear regression model, the nonlinear regression model looks like this. We have an endogenous variable on the left-hand side. We have an error term on the very right-hand side, ui. So these are as before, as we already know from the linear regression case. But in between, we have something which is completely general. So some kind of functional form of some kind of function of these regressors here. So it could be a linear function, it could be a nonlinear function, it could be anything. So we don't really specify how this function looks like, but the important point here is that we do not specify it as a linear function. So it could be anything, it's quite general. You will remember that in the linear regression model, we had a set of assumptions, 4 assumptions. And of course, we need assumptions for the nonlinear regression model as well. And the nice thing is that we can carry over most of these assumptions almost without any change. So the first assumption is really unchanged. It's exactly the same as before. It says that the expected value of the error term given the regressors is 0. Okay? So we do not have error terms which are larger than 0 on average in certain, or for certain combinations on certain areas of the regressors, and negative values in other areas, but we assume that the expected value does not depend on the regressors. Second assumption is exactly the same as before. We assume that the joint distribution of the regressors and the endogenous variable is IID. So for all individuals, firms, countries, whatever, for all entities that we are looking at in our cross-sectional data, we assume that they are identically and independently distributed. This assumption, as we have talked about before, normally rules our time series analysis. So if you're interested in that, you are invited to specialize more in econometrics. Assumption number 3, no outliers. So we formalized that in the linear regression model by stating that the expected value of the 4th power of the regressors and the error terms must be finite. That's a bit more complicated here, but we just kind of heuristically state that we assume there are no outliers. That's the essence, if you like, of this assumption. So if there are outliers, that means that a single value, which is really an outlier, can determine the outcome of the estimation in an undue way. All right. And assumption number 4, no perfect dependence. That's also very, very similar to the linear regression model, where we assumed no perfect linear dependence. We call that perfect multicollinearity. And again, this is not really specified here, but it says that, well, we need something like the non-multicollinearity assumption in a nonlinear model as well. So the expected effect of a change in the first regressor on the endogenous variable can be written in this way here. So we have the value, the expected value, the expected value of the y before the change. So that's really just what is stated in the definition of the nonlinear regression model. So this is the expected value of y given all the regressors before the change of the first regressor. And then we compare that to the value, the expected value of y after the change in the first regressor, keeping constant all the other regressors. We look at the difference, so that's the change in y, the expected change in y, if we change the first regressor from x1 to x1 plus delta x1, keeping constant all other regressors. So this is the expected change. Of course, we would estimate that in some way. We will talk about that later. We would estimate that by estimating the effect after the change and the value before the change, and then we have an estimated change. The important point here is that the marginal effect, so the change in y, depending or as a result of a change in x1, depends on the values of all regressors. That's new, because in the linear regression model, everything cancels out, and the value of the marginal effect is just constant. It doesn't matter where you're placed. It doesn't matter which values the regressors have. But here, the marginal effect of y on x1 depends on the values of all regressors. That's the new problem here. All right, and to talk about different approaches and to explain why using the multiple linear regression model is still a good idea, we simplify the setup a little bit, and we only, for a while, only consider models with single regressors. So that's, in a way, going back to the first lecture where we talked about the simple linear regression model with only a single regressor x. We go back to this setting, single regressor x and a single endogenous variable, but we give up the linearity assumption and we consider two different approaches. The first one is we use polynomials in x to model the nonlinearity, and the second approach is we use logarithmic transformations to model the nonlinearity. So we will talk about each of these approaches in detail. We assume, just for simplicity, to be able to write that down more concisely, we assume that we only have a single regressor, but we do that, I think, just after the study break. All right. Unless there are any questions, of course. That seems not to be the case. So we have a short break now and see you again in a couple of minutes.
Okay, welcome back. Let's directly go, or just take a couple of seconds to go back to your computers. And then let's continue with nonlinear models, in this case, containing just a single regressor. Let me just share you that screen window. There you go. So we said that we consider for now just a simplification, just to make it easier to see all the formulas and to review everything, to do that with a single regressor of interest. I'll do the first approach with polynomial regression, and then depending on how much time we will have left, we are going to switch over to Mr. Trede again, and he will do the approach on logarithmic transformations. Polynomials have the form, or the polynomial regression in X has the form that we have our dependent variable yi is now equal to something we already know, so beta 0 plus beta 1 xi. So that's just something we've seen here from day one on. But now we also add higher order polynomials to the regression. So we add, for example, squared terms, so beta 2 xi to the square, and we can add beta 3 xi to the power of 3, and so on, up until beta r xi to the power of r. So to the highest rank polynomial we want to add. Very often that is just a squared model or a cubic model. These are sufficient models in many, many cases. So many times this r here isn't that big as well. And in the end, we also add our error term. So that whole thing should look very, very familiar to you, because that is just a simple, that is just a multiple linear regression model. Now, not in the data only, not in the data themselves, but also in squares and other polynomial terms of the data, but still the model itself has a linear structure. On the left-hand side, we have our dependent variable. On the right-hand side, we have a sum of regressors with their respective coefficients. And we could rename this xi squared regressor to w, the xi to the power r regressor to z, and then we would have something that is completely a complete linear model, just the way we saw them before. So that is a very convenient way of looking at this type of nonlinearity, because that means that we can proceed the same way we did as in the classical multiple linear regression case. The interpretation of the coefficients is now a bit more complex, because we cannot just change a single variable, a single regressor by 1 unit or by some amount, and leave all the other ones constant, because they are perfectly depending on each other. The squared regressor, of course, is a function of our linear regressor here. So we cannot interpret this variable here in the same sense as we could before, but the regression function, it's not a regression line in here, of course, stays the same. Let's look at an example, Mr. Trede showed you before, namely that we look at the influence of the average income in a district measured in $10,000s per person, thousands of dollars per person, and we're looking at the effect of that income on the test score. And we can compare, or we can look at two models here. We might be interested in a quadratic model, then we model test score being equal to beta 0 plus beta 1 times the average income plus beta 2 times the squared income. That is a quadratic model. And we might also be interested in considering a cubic model if there are higher ordered polynomial relationships between average income and test score. We might also add this cubic term, average income to the power of 3 here. If we want to do that in R, there are two ways we might do that. The first way is to, first of all, create a new variable, squared income, for example, that is equal to average income to the power of 2, and then use that new variable average squared income in our regression. And the second possibility is to directly incorporate the polynomials into our LM function. But be aware that you cannot use just the square as an operator here, but you need to wrap around the capital I function around the squaring of your variable, or around the change of your variable. That allows you to directly put the squared income into the formula of the LM command. And if you do that, and if you run this regression, you see that average income has an effect. So we have an estimate here of minus 0.04. So we would obtain a function, a curve that is opens downwards, sorry. And we can see also that the p-value here, both of the linear term and of the quadratic term, is almost 0. So we have a highly significant linear and quadratic influence of the average income on test score. The t-value, we've seen that here before, of average income to the square is minus 8.85. So it's the point estimate divided by the standard error. So 0.04 divided by 0.0047. That is roughly minus 9. And we can, with this, directly reject the null hypothesis of linearity. Why can we do that? Well, the null hypothesis of linearity would mean that the coefficient of average income to the square is 0, because that in this model, that indicates linearity. Because if that coefficient is 0, then we only have a linear coefficient. That one could also be 0, but if that one is 0 as well, we still have a linear model. It is a horizontal line, but that is just a linear model as well. So with this t-statistics, we can directly reject the hypothesis of a linear model, and our estimated regression function now is 607.3 plus 3.85 times the average income minus 0.04 times the squared average income. To display this or to look at this, we we computed this model for our typical income range, so ranging from $5,000 per person per person and year up to roughly 60,000, and we see that this curve, at least up until here, fits very well to the points. It fits very well to the points in the upper right corner as well, but because it's a quadratic function, this one, after we are roughly 48,000, our regression turns and decreases again. So you can see here, with even further increasing income, we would expect, using this regression function, the test score to decrease again. Let's look at this more concrete. We have our regression function, and with a regression function, we can directly compute the difference in test score, so delta test score here, or the difference in expected test score here. And as we've seen a couple of slides ago, this difference can be directly computed by putting in an old value or of our regressor. So in this case, we are looking at a change at the expected change of test score if average income increases from 5,000 to 6,000. So from the regressor increases from 5 to 6. We put in our new value of the regressor, that is 6, into the equation, and subtract what we would obtain if we just put in the old value, which is 5, into our regression equation. So obviously the intercepts cancel out in the end, and we have 3.85 times 6 minus 0.04 times 6 to the square, so times 36, minus 3.85 times 5, and then minus times minus plus 0.04 times 5 to the square. And we obtain a difference in test score of 3.4. That is from $5,000 to $6,000 of annual income. So in this very left area of potential district income. So in this case, this curve is rather steep. So let's have a look what happens if our income changes from $25,000 to $26,000. That is from here to a little far further right. In this case, the curve is already much flatter. So what we would expect is a smaller difference, and what we obtain is in fact a smaller difference. The difference is only 1.7 points in test score. And if we increase our income from 45 to 46,000 euros, then we are exactly up here and we don't see any change anymore at all. And if we go even further to the right, so an increase from 65,000 euros to $60 to $66,000, we would obtain a decrease in test score by 1.7 points. But well, average income was just a variable that should measure that should be an approximation of how well can the kids be, are the kids supported by their parents, how well are their outside school learning opportunities, and so on. So what we really expect that we see a decrease in test score if parents earn more, or should we maybe in this case look at a different type of model? So look at a model that does have a monotonically increasing function instead of a function like this quadratic function that can and will decrease after a certain point. And that is where I go back to Mr. Trede, who is going to introduce logarithmic models.
All right, so we've seen that it's possible to use polynomials to approximate a nonlinear relationship between the x and the y variable in a certain range. And we've also seen that in that case, if you go outside that range or even at the tails of that range, then the approximation might give unreasonable results. So we now have a look at a second approach to modeling nonlinearity within the framework of the multiple linear regression model. And this second approach has to do with logarithms. So the second approach is not to use x and y directly, but to take the logarithm of x and or the logarithm of y. And why is that a good idea? Well, first of all, it is important to note that using the logarithm, or the natural logarithm, which we normally take here, means that you can approximate percentage changes of a random variable. And that is because if you look at the change in the log, say if you go from the log of x to the log of x plus delta x, then you can use the rules for logarithms, which means that the difference of two logarithms is the same as the log of the fraction. That is, if you go from here to here, you have x plus delta x in the numerator and x in the denominator, and then you can rewrite that as 1 plus delta x over x. So that's exactly the same, just by the rules of transforming the log. And then we can take a first order Taylor expansion of the log around the point 1. And if we do that, and this approximation will be quite close if we are near the point 1, say if this value here is small, if we take this first order Taylor expansion, then we will quickly see that this log can be approximated because of this Taylor series property by just delta x over x. And this is the percentage change. Okay, so the log difference is roughly equal to the percentage change of the variable. And if we put in two numbers, just to get a numerical example for that, let's look at the case where x is 100, and we increase that by 1% to 101, or by 1 unit in this case to 101. Then the difference of the logs is, well, 0.00995, which is roughly 1%. Okay, so we can see that if we difference is roughly the percentage change. And taking the log is very easy. You can just put in the log function in your computer code, and then what you get is the percentage change for that variable. Okay, if we go over to the infinitesimal small changes, we get the differentials. So you remember that if you take the derivative of the natural log, what you get is just 1 over x. And we can, in a way, rewrite that by moving the dx to the top of the right-hand side. And then what we get is the change in the log is dx over x. So this relationship is only approximate for finite changes. But if we go to infinitesimal small changes, it's an exact relationship. So the approximation here is only an approximation, but it's quite close. And the nearer we are to the 0, so the smaller the change, the better the approximation. So you can see here that for 1 percentage changes, the approximation is almost perfect. If you go to 5%, then it's still very good. If the change becomes larger than, say, 10%, then the approximation gets poorer. And if you have really large changes, then it doesn't work anymore. But for small changes, this approximation is really excellent. So that's the idea here. And we now simply substitute one or both variables in our regression model by the log values. So we have three specifications. There's actually no standard terminology for them. So we just included here two names for each of them. The first specification only takes the log of the regressor. And we call that the linear log model because the left-hand side is still linear in a way, and the right-hand side has the log here. In other books, it's called the semi-logarithmic model, but we call it here the linear log model. So we only substitute x by the log of x. Then we can do the same on the other side. So in that case, we will talk about the log linear model. Sometimes it's also called the exponential model. And here we take the log of the y variable, but not of the x. And finally, the third specification is the log or logarithmic model, where we take the logs both of y and of x. Okay, so we have three different specifications. The fourth one is just the linear model. That's the simple linear regression model that we had before. No log and y, no log and x. But then we have three different models, as you can see here. All right, let's look at each of these models in turn, and let's start with the linear log regression model. So we do not take the log on the left-hand side, that's the linear part, but we do take the log on the right-hand side, that's the log part of the linear log regression model. What's the change of y in this model if we change x by 1 unit, or by delta x in general? So if we change x by delta x, then on the right-hand side, we start off with the log of x, and then we go over to the log of x plus delta x. On the left-hand side, that induces a change in the endogenous variable y. So we start at y, and then after we change the x, we get a new value on the left-hand side, and the difference between these two values, the old one and the new one, is delta y. So this is, in a way, the definition of delta y. So we can now reformulate this model and subtract the first equation from the second equation. In that case, on the left-hand side, if we subtract the y from y plus delta y, what remains is only the delta y. On the right-hand side, beta 0 minus beta 0 just drops out. That completely vanishes. And here we have beta 1 log of x plus delta x minus beta 1 log of x. So in that case, this is the difference. And in here, in this bracket term here, you can see that we have exactly the expression that we talked about before in the previous slide. Therefore, this can be approximated, this log difference here can be approximated by the percentage change. So the whole term can be expressed at least approximately, and with a very accurate approximation for small changes in x, by beta 1 times the percentage change of x. And now we could remove or move over the percentage change to the left-hand side and then rewrite the whole thing, and we can see that the marginal effect of change in x on y is no longer delta y over delta x, but delta y over delta x over x. So it's not the change in y, the unit change in y as a response to unit change in x. Now it is the unit change in y as a response to the percentage change in x. So a relative increase of x by 1% results in an absolute change of y by, well, 1% times beta 1, okay, in the linear log model. And this approximation is very close for small percentage changes of 1, 2, 3, 5%, maybe 10%. So a simple example, let's assume these are completely arbitrary numbers. There's no real meaning to that. That before the change, we had an intercept of 5, a slope coefficient of 0.2, and an x value of 3. So in this case, we can just type this into our calculator, and we get 5.219. Then we increase x by 1%, from 3 to 3.03. We compute the new value of y, which gives us 5.2217. And the difference of the new value minus the old value is 0.00199, which is roughly 1%, because we increased x by 1% times beta 1. And beta 1 is the slope coefficient here. Okay, so that's the change. The interpretation of beta 1 is tells us what the absolute change in 1 as a response to 1% change in x is. All right, here we do that in R. So we compute our regression object using the linear model command. On the left-hand side of the formula, we have the test score. And on the right-hand side, we do not include the average income, but the log of the average income. And in contrast to what you've just seen for the polynomial model, you do not need this capital I function here. So just really type in log of average income. The only difficulty here, difficulty is that log is the natural log in R. So you do not type in ln. All right, then we compute the usual table for the outcomes, and using the heteroscedasticity robust estimation, and we get this estimate here, and the slope coefficient 36. So this is the beta 1, which means that if we increase average income by 1%, and this could be quite different absolute changes, because if you increase it at a level of 5,000, the 1% change is in absolute terms much less than if you increase an average income of, say, 40,000. So the slope coefficient for the log average income is 36, which means that an increase of 1% of average income will result in 0.36 more points in the test score. That's the first of the 3 models. Now let's go over to the second one. Now we do the same derivation. We start with the log linear model. We change x and look at the change of y. So the change of y is now inside the log. We can rewrite that new value minus old value. So on the left-hand side, we have the log change in y, and on the right-hand side, beta 0 drops out, and beta 1x also drops out, and what remains is just beta 1 times delta x. We can approximate the left-hand side by delta y over y, as we have seen before. So beta 1 is the percentage change in y divided by the unit change in x. So an absolute increase of x by 1 unit, results in a relative increase of roughly beta 1 times 100%. Okay? And you might have heard that, especially useful in monetary economics. You might have heard the expression semi-elasticity. So what's the percentage change as a response to a unit change in the other variable? That's called a semi-elasticity sometimes. And in this case, beta 1 is just a semi-elasticity. And the approximation is very close, as usual, for small percentage changes. So let's look at an example again. On the right-hand side, we have an intercept of 1, slope coefficient 0.2, and 2 values 3, and we move that up by 1 unit to 4. We look at the change in y, and we can see that the change is roughly 22%. So you can see here that 0.2 is, roughly, approximately the unit, the response of y, the percentage response of y if we increase x by 1 unit. Right, that's the second case. And now let's go over to the last case, the log regression model. That's quite common in economics, and you will see in a minute why that's the case. And now we take the log on both sides of the regression equation. On the right-hand side, we don't include x but ln x, and on the left-hand side we have the log of y. Now we change x and look at the change in y. We change x from x to x plus delta x, and we expect y to change as well by delta y, and we want to know what is delta y. Okay. We again subtract the first equation from the second. So on the left-hand side, as before, we have the log difference in y. On the right-hand side, beta 0 drops, and we get beta 1 times the log difference in x. We can approximate the left-hand side by delta y over y, and we approximate the right-hand side by delta x over x, and therefore we can rewrite the entire expression and state that the marginal effect beta 1 is the percentage change in y over the percentage change in x. Now this rings, and you will remember that a relative increase of x by 1% that results in a relative change of y by approximately beta 1% means that beta 1 is an elasticity. That's the very definition of elasticity. What's the percentage change in one variable in response of a 1% change in the other variable? So here, beta 1 is just an elasticity. And the interpretation is just as you have learned that in microeconomics, or maybe also in macroeconomics. And as usual, the approximation is very close for small percentage changes. We can see that here in this simple example, where we increase the x by 1% from 3 to 3.03. And we look at the change in y, and we can compute the change in y is 5.1%. Okay? And that's not surprising because the slope coefficient, the beta 1 is 5, so it's 5%. All right. And we can run that as well in R. So here we have the relationship between the log test score on the left-hand side, and we model that as a function of the log average income on the right-hand side. We just use the ordinary LM command. We do not need the capital I function. We only need that for polynomials and some other transformations, but for the moment it's only for polynomials. So here we just include log of test score and log of average income. We have our regression object, reg-R, and we use the KOF test command to find the standard errors and the t-values and the p-values. So here we have this change. All right, so to sum that up, we can transform both the x's and the y's by taking their logs. And in that case, the regression is still, in a way, a linear regression because it's still linear in the generated variables, so log of x and or log of y. So the estimation approach is just the same as before. We still use the LM command in R. The entire test theory does not change. So we can perform hypothesis tests in the same way as before. And also, the inference for, say, confidence intervals is really unaltered, and we can just use the same approach as before. The only difference depends on the type of model that we work with. So is beta 1 a semi-elasticity, an elasticity, or does it say what is the change, the unit change in y as a response to percentage change in x? All right, and one final point for today, and we are just running out of time. The question is, could we use if we want to decide which of the four models that we've got, the linear model and the three models I've just introduced, can we use R square or the adjusted R square for model comparisons? And the answer is yes, but only to a limited extent. We can use the R square to compare two different models if the left-hand side is the same for both models. So if we can compare the first two and we can compare the second two by looking at the R square, we can, for instance, say that if we compare the first two models, the second one has a better fit, and also in the for the second two models, the second one has a better fit. But we should not compare the second model to the last one, or the first one to the third one, or to the last one. So R square is only useful for comparisons if the dependent variable is the same, because R square gives us the variation, the share of variation that we can explain, and of course the variation should be the same, so the left-hand side should be the same. So that's roughly it for today. We continue talking about nonlinear models next week. So there's a third approach to nonlinearity apart from polynomials and log transformations. But unfortunately, Andreas won't be here next week. So let me just say thank you very much. It was a pleasure to work together with you, not only in this course, but in other courses before as well. And I think I will really miss you. And I think the students will miss you as well. So thanks again. And bye-bye to the rest of you. And see you next week. Bye-bye. Thanks.
Thanks from my side as well. I enjoyed working together as well. I liked the lectures. And yeah, bye. And all the best to you, all the students.
Thanks.